This video looking at electrons in the periodic table. They really go together. We're going to talk a little about the Bohr model and Lewis models and the drawings, but really focusing a lot on electrons. And then we're also going to talk a little bit about our periodic table and talk about some areas on the periodic table and give you a cheat to help you draw these. So electrons are going to be really important for what we talk about. They determine an atom's reactivity and behavior, which really that's what chemistry is how you react with something, how you act and interact with other compounds, mixture, atoms, stuff like that. Something to think about. So why, when you take a piece of iron and throw it in a fire, if you're using like your hot dog poker or something like that, why is it that eventually it starts turning orange? And what can, using what we know about the atom, how can we explain this? This is kind of what the question Bohr had and where he came up with his model. So, quick review. This should be in your notes. This is from Atomic History Part 2. But his solar system model, he said electrons have to be in these orbits around the nucleus. And he said each of these orbits has a different amount of energy. The further you are from the nucleus, the higher energy that orbit is. So energy levels we'll talk about, especially coming up here when we get to electron configurations. But in the Bohr model, that's the layer or the shell. Which shell are we talking about here? Bohr, so using something called, he quantized energy. So he said that electrons can gain or lose, which means move up and down the ladder, if you want to think of it that way. But they have to be on one of the steps, or they have to be in one of those orbits. So these certain values, we say energy then must be quantized. So it has to be a certain amount. Using this idea, he correctly predicted the behavior of hydrogen and how hydrogen, when you stick it in a fire, it gives out a certain color. He was able to figure out where that came from using this idea. So, quantum of energy, required amount of energy to move from one energy level to another. So this is a packet of energy, which it means it's a very specific amount, is what we mean by quantum or packet of energy. And just remember, electrons have to be on one of those steps, one of those rings. So Bohr's model looks like this. And this is a better picture than what we drew before because it shows that to go from a 1 to 2, or 2 to 3, or 3 to 4, it actually takes different amounts of energy. So a bigger or smaller sized packet, or quantum. So the further you go out, it doesn't take as much energy to go to a 3 to a 4. Is what's important here. What this allows us to do, and what this told Bohr is, well, okay, we have these electrons, they have to go somewhere. Well, how do I know where they start? So this is called the off-bow principle, and what it says is electrons start or fill the lowest levels first. Once they are full, then we fill the next one. Once it's full, and so on, we keep moving out. So put electrons in the inner circle first, and then move them out. What I want to do here is draw the Bohr model for aluminum. I just picked a random element. Couple things you need to know. One, how many electrons does that element have? And then two, how many electrons can I put in each of these rings? So, and this is true for all elements in terms of how many you can put in there. So first, figure out how many electrons. Go to my periodic table, see aluminum. It doesn't tell me it's an ion, so atomic aluminum has an atomic number of 13, which means I have 13 electrons. So how I'm going to put these in the model is, well, the first orbit, so the first ring is going to hold 2 electrons. The second ring can hold 8. So now I'm up to 4, 5, 6, 7, 8, 9, 10. Alright, so I got 2 in the first ring, 8 in the second. So that's 10. It's full. Now I got to move to the third one. 11, 12, 13. Notice I did put third fits up to 18. There's some weird things that happen that, again, this is why the Bohr model isn't exactly the greatest. We'll give you a cheat to figure out exactly how these fill once we get to these outer rings. And eventually we won't even draw we won't draw Bohr models for bigger elements just because it doesn't make a whole lot of sense once we get so many electrons. But again, 2 in the first ring, 8 in the second. So once that was full, I moved to the second one, put my 8, it was full. I moved to the outer one to finish up to get those extra 3. So that is the Bohr model for aluminum. Notice I didn't even have any in the fourth ring. I didn't need that space. You just keep filling. Alright, so where we just put the electrons, this is called the ground state. So this was the lowest possible places I can put each of those electrons. Just remember though, we can give electrons energy, either putting them in a fire, charging them with some electricity or something like that. When we do that, they become excited. We call this the excited state. Kind of makes sense. Ground state, low energy. Excited state, high energy. Going to take a step back for a second from those models and just want to talk about our periodic table a little bit. Really just so we can talk about the outer electrons, but it's good to know some of these spots on the periodic table just so we can kind of communicate. And I can say, you know, the alkali metals or the halogens or something like that, or the S block. It'll just allow us to talk about things a bunch of different ways. We'll get way more into these blocks later on this unit. So, a couple areas on the periodic table you need to know. If you remember, there were 4 different types of orbitals for the quantum mechanical model. These go right along with it. The first orbital we drew was the S orbital. If you remember, it was just the sphere shape. There was only one picture, only one drawing of the sphere. Each drawing holds 2 electrons. So notice 1, 2. There's 2 electrons. So this is called the S block. Holds up to 2 electrons in each row. Get there in a second as well. The next drawing you drew the P block, which were kind of the double balloon shapes. What kind of like dumbbells or Q-tips or something like that. But if you remember, you drew 3 different pictures of those. And okay, so there were 3 pictures. Each picture holds 2 electrons, so that's 6 on my periodic table. 1, 2, 3, 4, 5, 6. This is the P block. So each P orbital holds 6 valence electrons. We said this is the P block. The next set of shapes you had to draw was the D orbitals. If you remember, there were 5 different pictures for those. So 5 times 2 gets me 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This middle part is the D block. And the last one, the F block, we didn't draw them because we said they were just crazy ridiculous shapes. But if we were to draw them, there were 7. 7 times 2 then, so each of them hold 2, that's 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is your P block. So just a couple areas on the periodic table and how they relate to the quantum mechanical. We'll get more into that later. Just know where the areas are for right now. Next thing, groups and periods. So certain columns have specific names, and this again just help us communicate back and forth. But something first maybe you need to know is groups you might hear called families. People use both terms. You'll see them both. What you need to know though, groups and families, they run up and down. So they are columns on the periodic table. Periods run left and right. So the first column, that's a group. The second column is a group. The first row would be a period. So some specific names. If we leave out hydrogen up here, this first column is called the alkali A-L-K-A-L-I, alkali metals. The second column is called the alkaline earth metals, so A-L-K-A-L-I-N-E, alkaline, I'm going to run out of room, E-A-R-T-H, alkaline earth metals. Our D block in the middle doesn't really have anything fancy other than that. Over here in the non-metals, we have the halogens. And our last column here, hopefully you've heard of these, the noble gas. Oops. The noble gases. So just a couple of names on our periodic table. The other thing is you are going to see something called a principal quantum number. This is just how we number periods. And for these we use n. So n equals 1, n equals 2, n equals 3, and this is for each row. So 4, 5, 6, and 7. These are the principal quantum numbers, or again, how we number periods. This sheet is going to be something you're going to use a ton. So how many valence electrons do each of these columns have? So something you're going to learn is all groups have similar properties, and that's because they have the same number of valence electrons, and we'll define that word here in a second. But while we got our periodic table out, so number of valence electrons. Our alkali metals have 1 valence electron, by abbreviation Be. These guys, our alkaline earth, have 2 valence electrons. This column, so we're sticking with the columns that stick up higher than the rest of our periodic table. These guys have 3, 4, 5, 6, 7, and 8. So every one in this column here has 8 valence electrons, except the top guy here, helium. He's just too small to hold 8. He only has 2 valence electrons. That's our one exception to this rule. D block, we're not really sure. Our P block, our F block, we're also not really sure either. All right, Lewis, 1920s, he thought these valence electrons were pretty important. So he focuses his model on those valence electrons. So our definition of valence electrons, they are the outermost, they determine the properties of the elements, and they are involved in bonding. So this is why he thought they were important, and he was definitely correct. These are the electrons in the outermost orbit of Bohr. So if we go back and look at our aluminum, notice 3 electrons out here in the third ring. Those are the 3 valence electrons for aluminum. If we go and look, aluminum is right here on our periodic table. It's in that 3 column. We could have predicted that before. So let's draw the Lewis dot models. These are super easy, especially if you have that sheet. We know, because we saw the Bohr model, aluminum, let's go red so you can see it. Aluminum has 3 valence electrons. If you use the cheat, lithium has 1 valence electron. Magnesium, 2 valence electrons. Oxygen, out in column 6, has 6 valence electrons. So watch how I do this. 1, 2, 3, 4, and then I go back through and pair. So 4 sides, and then I go back through and pair them up. 5 and 6. So it has 2 that aren't paired up. Always do that. It's going to make this a lot easier later on if you learn to do it correctly here, because when we start putting these together, it's going to be a problem. Fluorine then has 7. 1, 2, 3, 4, 5, 6, 7. And that is it.